Hello, everyone. My name is Ariana Gonzalez. I am an undergraduate physics major at the University of Florida. And today I'll be talking to you about the research that I'm conducting with Dr. Darren Acosta, which is the data analysis study to identify possible new Axion-Like particles in a Higgs boson decay. So let's begin. All right, so what are axion and axion-like particles in the first place, right? So an axion is a hypothetical elementary particle that's used to resolve the strong CP problem in quantum chromodynamics. And an axion-like particle are similar to axions in this case and would have similar properties to them. If axions would exist, they would have a low mass within a specific range, and they are of interest to us as a possible component of cold dark matter. Overall, let's just define some of these terms here. So quantum chromodynamics, right? Or QCD. So QCD is the theory of the strong nuclear force that binds together nuclei. And the strong CP problem is a problem or conundrum with the theory that requires a new particle in order to naturally explain symmetry in the theory. Overall, since the Higgs boson does connect to the electroweak theory, this explains why particles gain mass, because the Higgs boson is able to couple to particles in order for them to have the property of mass. So in this case, this axion-like particle, if it has mass, the Higgs should be able to couple to it, which is why we're looking at the specific decay. All right, so what is the significance of this research? So this research attempts to review and optimize the steps required to conduct a search for new axion-like particles in a Higgs boson decay. So this would be a Higgs boson that decays into a Z boson, an axion-like particle that decays into 2 leptons and 2 photons. And we're trying to assess the sensitivity of such a decay. This analysis uses proton-proton collision data from the CMS detectors of CERN's Large Hadron Collider to search for the decays. This presentation will be explaining my proposed research and what it entails overall, as this research is still in progress as well. So now for some background. So CERN is located in Geneva, Switzerland, which is where the LHC, or the Large Hadron Collider, is located. The LHC is the world's largest and most powerful particle collider, producing up to 13 TeVs of energy. The LHC collider has 2 high-energy beams that travel at relativistic speeds. They are guided by a powerful dipole magnet that produces a strong magnetic field that bends the trajectory of the particles. The particles then collide as they're traveling around the LHC, and the data from their collision is collected and sorted. CMS, which is the compact muon solenoid, is a general detector at the LHC. All right, so here are a few diagrams of CERN and the CMS detector itself. So overall, you can see here's the CMS detector on this area. There's also accompanied by a few other detectors such as the Atlas, LHCb, and Atlas detectors. Over here, you can see the transfer slide of a compact muon solenoid. So from here, a particle will start out towards the center, towards the silicon trackers. And here they will measure the particle's trajectory and momentum. Then it will travel towards the ECAL, or the electromagnetic calorimeter. And this is where they're going to stop a few particles in their tracks, such as electrons and photons. And then from there, they would measure their energies. Then likewise for particles that contain quarks, for the hadron calorimeter, they'd also stop it in its tracks and measure its energy. Then other particles such as muons and also neutrinos would keep on traveling out. Muons would be detected from these muon chambers or muon detectors. Overall, these are composed of drift chambers and also cathode strip chambers as well. And they are recorded for their momentum and also just overall trajectory. Neutrinos just keep traveling out. They don't really interact too much with these, but they're calculated in missing energy, or missing transverse energy in this case. And over here, you can see it's kind of a similar process, except everything starts within. Towards the center, particles will be traveling outwards overall. And yeah, that's how it works so far. All right, so for research progress so far, we are currently in the process of creating a few histograms, plotting simulated data from an n-tuple. So also just for background, an n-tuple is just a data file that of a specific format in this case. So these events are also simulated with Delphis. Delphis is a simulation of a general detector in the LHC. There will be histograms of the dileptons that would show the invariant mass, energy, and transverse momentum of the dileptons. Additionally, there will be histograms of the diphotons showing the invariant mass, energy, and transverse momentum. So what's next? So I want to become more involved in the data selection process where selection requirements are applied to the data. Then afterwards, we'll be validating the data in comparison to the Monte Carlo simulations in control regions to ensure the backgrounds are understood. Then we will be studying the possible systematic uncertainties that can affect a search. And finally, we will see how the results are interpreted as limits on cross-sections and theoretical parameters. Overall, will be investigated as well. All right, so that concludes this presentation. I would like to give some thanks and acknowledgement. So I would like to thank my mentor, Dr. Darren Acosta, for his guidance throughout this research. Additionally, I would like to thank the UF CMS graduate researchers for all their help and assistance throughout this research too. I would also like to thank postdoc Dr. Kinho Lo for his guidance and feedback during my research. Finally, I would like to thank the UF McNair team, Dr. Barnes, Dr. C, Dr. Helwig, and Mrs. Hechevarria for all of their assistance. Thank you.